Welcome to EDU World Space.
In this video, we'll be using Simpson's rule to find some surface area obtained by rotating a curve around the x-axis. So we ought to use the surface area formula first, which is the following. 2 pi y, the square root of
Here's
1
a clean and
plus
professionally formatted
y
presentation
prime
of the
squared
calculation shown in the image.
dx. So here's what we need to
Application
do.
of the work energy theorem.
Let's first set up the
wet.
integral.
From the work energy theorem, the force F is given
And then
by
we'll talk about
F
the
equals
Simpson's rule.
frac text KE,
With that
where
being said,
KE
given a
equals
curve,
kinetic
y
energy,
equals x
S
times
equals
e
stopping
to the
distance.
x,
Then
we know
given
its
for object
derivative
A,
by
FA
using the
equals
product
frac
rule.
100,000,
It will be equal
0.10.
to the
For
same
object
term
B, FB equals frac
with an additional
225,
factor of e to the
1500
x.
equals 0.15 text space n.
And we can
force ratio
substitute
frac
all of this
FA,
into our
FB
integral.
equals
And I
frac
forgot the actual
0.10,
range of integration that we're going to be using,
fractional result. A box
which would
frac
be
FA,
from
FB.
in between 0 and
Would
1.
you like a PDF version of this explanation?
So our integral will be the integral from 0 to 1. We'll have 2 pi y, which is x times e to the x times the square root of 1 plus the derivative squared, x times e to the x plus e to the x, the whole thing squared, dx. So this is our integral. So what I'm going to do is I'm going to let the entire integrand be equal to f of x. This will just make our work a little bit easier. Now for Simpson's rule, the approximate area under some function will be equal to the change in x divided by 3 times, we would have f of x naught plus 4 f of x1 plus 2 f of x2 plus ... and so on until the pattern continues. Xn minus 1 plus f of xn. In general, we'll be using this formula. And remember that delta x would be equal to b minus a divided by n. In our case here, we have that x is going to be in between 0 and 1, and we're asked to use 10 subintervals. So we're going to have 1 over 10, because the last bound is just 0, thankfully. I'll write it as 0.1. So what this means is our integral will be approximately, using what we had obtained earlier and substituting values of the specific function, we're going to get that this is equal to approximately 0.1 over 3 times, we would have f of 0 plus 4 times f of 0.1 plus 2 times f of 0.2 plus 4 times f of 0.3 plus 2 times f of 0.4 plus 4 times f of 0.5 plus 2 times f of 0.6 plus 4 times f of 0.7 plus 2 times f of 0.8 plus 4 times f of 0.9 plus f of 1. And you would use, again, as said earlier, you would substitute these x values into the integrand and then determine what the value would be from there. And when you do that, you're going to get that this is approximately going to be 24.1443. So that's the approximate value. But we want to compare it to the absolute value, or the correct value. And obviously this integral is pretty hard to evaluate by hand, so we're going to use Wolfram alpha for this. And when we do so, when we use Wolfram alpha to evaluate this integral, we get exactly 24.1443. Actually, when we actually do the approximation, we get about 24.1458. That's how you do this problem.